So, we are going to start off today talking about what is called the electromagnetic spectrum. Alright, which includes multiple types of electromagnetic radiation. And just to help you get your bearings on this graphic, which should look somewhat familiar, you should have seen it in Chem 1. The numbers running along the top are wavelengths, because these are all things that travel in waves. We have very small, short wavelengths on the left, and very large, long wavelengths on the right. Okay? And I often think of this chart, okay, it's not a perfect relationship, but extreme danger to living things, less danger, or virtually harmless, actually. There's a lot of real-life application here, okay? Gamma rays, that should be familiar to you. Back in Chem 1, we talked about nuclear radiation. Do you remember alpha, beta, gamma decay? All right? This is a type of radiation that is released when things go through nuclear decay. Very easy example. Let's think about our history. End of World War II. The United States drops 2 atomic bombs on Japan, and they were nuclear reactions, chain reactions. And there's a lot going on in a nuclear bomb, okay? The people that were in the immediate vicinity of the drop site, many died from the shock wave, others died because a building fell on top of them. Some of them were exposed, and I'm sure you've seen pictures of this in textbooks, were exposed to so many gamma rays that they were actually like vaporized instantly, okay? But people that survived the shock wave, or a building didn't fall on top of them, and they were farther away from the drop site, okay? These people were still exposed to a massive amount of gamma rays. And gamma rays, ladies and gentlemen, are extremely dangerous to humans, okay? They carry a lot of energy with them. They can pass through the human body, and when they do, they tend to target your DNA. Now think back to biology. If something is attacking your DNA, do you think that's a good thing? No. That is a very bad thing for your health. But people, guys, that survive these blasts, if your DNA is being attacked, most of these people died of cancer. Okay? When you start making changes in DNA, that almost always will lead to some form of cancer. And even in the United States, my great-grandfather is an example. He was one of the scientists who worked on the Manhattan Project. Okay? Out in Los Alamos, New Mexico, these scientists out in the desert did these tests to develop these atomic bombs, and most of these scientists, my great-grandfather included, died of cancer because they were so exposed to these gamma rays. Okay? Let's move a little bit further to the right. Are X-rays dangerous? Yes. Okay? I would imagine most people in this room have had at least one X-ray, yes? Okay? When you go in for an X-ray, are you exposed to those X-rays for very long? No, like less than a second, okay? And let's say you're getting an X-ray, like you've broken your arm. You're getting an X-ray of your arm. They make you wear a cover on the rest of your body. Do you know what that cover is made of? Lead, okay? X-rays cannot penetrate lead. They don't pack enough punch. They don't have enough energy to get through it. Okay? Now, are X-rays dangerous? Yes. Okay? Which is why you want to minimize your exposure to them. But I'll tell you that the scientists that created the X-ray machine for the medical community died of cancer. Right? Science is dangerous, people. Do it at your own risk. Ultraviolet. What time of year do we hear about this a lot? Summer. Can ultraviolet light hurt you?
Yes.
Yep. It can burn your skin. If it's shined directly in your eyes, it can burn your retina. It can cause skin cancer. Okay. How about visible light? Dangerous? No. I do want you to remember, though, that blue light, violets, okay, those are the ones with the shorter wavelengths. Oranges, reds, those have the longer wavelengths, okay? And guys, this whole, like, dangerous, not dangerous, it's not perfect, okay? Visible light cannot hurt you, okay? But we will see some things that can, okay? Infrared light, if you ever are using your remote for your TV, when you push any button on your remote, on the very end, there'll be a tiny little red light that comes out. That's infrared. If any of you have ever been to a restaurant that has one of those open kitchens where you can see the chefs doing their thing, sometimes the chef will put together a plate, but it's not ready to go out to the table yet. They'll put it under a red lamp. It's called a heating lamp. It's just infrared light. Okay? Keeps it warm. Microwaves. Okay? And guys, I don't mean microwave ovens. I mean microwaves. Okay? And this gets into our essential question for the day. Why shouldn't you put your pet kitten in the microwave? But ladies and gentlemen, if somebody had some kind of special, like, science fiction laser gun that fires microwaves, if someone fires a microwave at you, it's not going to be a real problem. Why is it that putting a living thing in a microwave oven is dangerous? Okay, we're not talking about just one microwave. We're talking billions, trillions, maybe more than that, all being fired at the same time. And not only being fired at the same time, but being fired at sort of a centralized area in the space of your microwave oven. Okay? And in case you don't know, a microwave works by the fact that a microwave is at a certain wavelength that reacts with water. Okay? And any water molecule that's in whatever's in the microwave will start to shake. And when water molecules start to shake, the temperature goes up. Sometimes high enough that the water will actually boil. Imagine how much water you have in your body. What are we, like 80% water? Okay? Give or take. What about your pet kitten? Got water? Pet kitten definitely has water. Okay? If you put pet kitten in the microwave, and pet kitten's little water molecules start to shake and heat up, and then start to boil, alright, you got a mess on your hands. Okay?
So,
we're not going to do a live demonstration, okay?
oh God.
Yes, Ava?
Is it dangerous to like microwave something without anything in the microwave?
Good question. I was just going to get to that. Okay? So guys, if a microwave works by agitating the water molecules, okay, in theory, and I say in theory because when I said this yesterday, somebody went and did this and then burned their hand. Please don't do this, okay? In theory, if you put something in a microwave that contains no water, like, let's say, an empty ceramic coffee mug, fine. You put it in the microwave for 10 minutes. In theory, at the end of that 10 minutes, it should be just as cool as it was when you put it in. There's no water in there. However, and this is what this person in my class yesterday failed to hear me say, ceramic is a here's a word we've used before, a hygroscopic material. What does that word mean? Absorbs water from the air. Okay? So it may feel dry, but it does have a tiny, tiny, tiny amount of water, and even just a tiny amount will cause that ceramic to heat up. Okay? If it was totally dry, though, it should not heat up. At the end here, we have radio waves. FM shortwave, AM radio waves. Please don't ask me where, like, Sirius XM falls in there. I'm not sure. Someone asked me last class where cell phone waves fall in, and I want to say I'm not exactly sure, but somewhere in here. Okay? And that's why there is still some debate out there as to whether people who are constantly using their cell phones are exposing themselves to dangerous radiation. The jury is still out on that. Okay? But, okay, if you're in your car and you're listening to a radio station like DC 101 or WMZQ or whatever, an FM station, okay, the radio waves that are hitting the antenna of your car have a wavelength of about a meter long. Okay, now most of us probably don't listen to AM too often. It's a lot of like gospel music and opera and talk radio and smooth jazz, you know. Maybe that's your thing. I don't mean to put it down. All right, but look at that number. That's big. Okay, AM radio waves, guys, have wavelengths close to a mile long. Okay. And by the way, what is a wavelength? What distance is that? From what to what? Crest to crest, peak to peak, or trough to trough, valley to valley. Okay? And I want you to try a little experiment. Okay? The next time you are in your car and you go into a parking garage, let's say like one of those above ground ones, say at Tyson's, for example. If you have on your radio an FM station and you go into a parking garage, which is made of predominantly concrete, you will probably be able to keep an FM station, meaning it won't go to static. But if you have an AM station, even in an above ground parking garage, because there is so much concrete, you will probably immediately lose the station. Because these waves, and I have kind of danced around this topic a little bit, they carry very low amounts of energy. Okay? They can't penetrate through concrete. Okay? FM waves carry a little bit more. Alright, and so they can get through some. If you go into one of those below ground parking structures, you're definitely losing this one. But you're probably also going to lose that one pretty quickly because there's just too much concrete to get through. If any of you have ever been on the metro, you often will lose your cell reception. Same kind of deal. Okay? Same situation. So we're talking about wavelengths here. We've talked about energy. What kind of energy content are we talking about at this end? High or low? High, lower down at this end. Okay. So what kind of relationship does wavelength have with energy? If wavelengths get shorter and shorter and shorter, what happens to the energy? Gets higher. What kind of relationship is this? Inverse. Okay. Something else to talk about. Frequency. Okay, should have talked about that in your Chem 1 class. It's the number of waves that pass a certain point per second. How are these related? If I have a very small wavelength, what kind of frequency am I looking at? High. So that's another inverse relationship. What kind of relationship do frequency and energy have? Direct. The higher the frequency, the higher the energy. Do you remember from your Chem 1 class what all types of electromagnetic radiation have in common. Yes, Alba? Speed of light. They all travel at the same speed. You do not need to memorize that number. It is on your equation sheet. Okay? And let's look at another equation. Okay? By the way, I want to say that the next couple of slides have multiple equations on them. Do not worry about writing them all down. They are all on your equation sheet. Nothing to memorize. Okay? This is a relationship between wavelength, that's lambda, and frequency, which I can never remember what Greek letter that is. It's not V. What is it? No, it's a Greek letter. Like this is lambda, this is... I can't remember. Anyway. Okay, but that's frequency. Now, people keep asking me, well, can't we just put it as a letter F like we do in physics? Chemistry and physics like to have their own set of variables. Don't ask me why we have to make things more complicated. Okay, I have no idea. C is the speed of light. Okay, let's talk units for a second. Wavelengths always need to be in meters. Speed of light is always going to be in meters per second. Frequency is in units of inverse second. What's another way to say an inverse second? Hertz. Okay? 1 hertz, sounds kind of weird to say that. 1 hertz is equal to 1 inverse second. 1 wave, 1 cycle per second. Okay? Now, there's one other characteristic of a wave I want to talk about. What is this called? The height of a wave. What's it called? Amplitude. Okay? I just want to see how many of you know this, just totally out of curiosity. Let's say we are talking about a sound wave. Those of you that are musically inclined will probably know the answer to this. If you change the frequency of a sound wave, what are you changing about that sound? The pitch. Okay? If you play a very high note on a violin, that's a sound wave that has a very high frequency. Low notes have low frequencies. Let's continue with the sound wave. If you change the amplitude of a sound wave, what are you changing? The volume. Okay? The volume, the loudness. Okay? Let's talk about not a sound wave, but a light wave. Visible light. If you change the wavelength, which is in turn also changing the frequency, what are you changing about that light? The color. Short wavelengths, high frequencies are going to be blues and violets in color. Long wavelengths, low frequencies are going to be reds and oranges. What are you changing about a light wave if you increase the amplitude? Someone said it. The brightness. Any of you have dimmers on your light switches at home? That's what you're adjusting, is the amplitude of the light wave coming from your light source. Okay? All right. Here's another equation, set of equations. Don't write it down. Don't memorize it. It's on your equation sheet. This is how you would calculate the energy of an electromagnetic wave. E is energy in joules. H is a constant, folks. It's called Planck's constant. It's on your equation sheet. Okay, this is still frequency. This is still wavelength. This is just another option of an equation you could use. And I want to make something clear here. All right? I want to preface what I'm going to say next by telling you that chemists and physicists have very different thoughts on the next topic. So what I am going to tell you is the chemistry side of the story. If you go to physics, your physics teacher may very well say, no, that is a load of baloney, and here's why, and then they're going to prove it to you, and then you're going to come back to me and you're going to say, my physics teacher proved you wrong, and then I'm going to show you something that proves them wrong. Okay? It's a theory, guys. It's a theory. And we have sort of different views on this. Here is the deal. Okay, I keep saying electromagnetic radiation travels in a wave, travels in a wave. What travels in a wave? Air? What? Photons. Okay? The word photon is a shortening of a longer word. Do you know the longer word? Photo-electron. Ladies and gentlemen, a photon is an electron. Tell me this. Does an electron have mass?
Yes.
See? Here's the argument right here. Those of you that said no or negligible, you are on the physics side of the fence. And you can leave. No, I'm kidding. I'm kidding. Okay? Does an electron have mass? Chemistry says yes, it does. Okay? Does it have a lot of mass?
No.
No. Okay, but it does have some. And Einstein's famous equation says that anything that contains energy, like all of these waves we've been talking about, have mass. And he's the physics guy. He's saying that. Come on, physics, get on board. Okay? But they're going to show you some mathematical equations that prove that anything that has energy doesn't have mass. And I have my own equations that prove that it does. You choose which side of the fence you go on. So this is an equation you can use. It's Einstein's famous equation. Here are some other ones you could use. Don't memorize them. They're on your equation sheet. Now, this is when I get to use some of my fancy technology. Alright, this is a graphic from your textbook. And I'm not crazy about it because I think it gives kind of a misrepresentation. It says light is a wave. Light is also has particle aspects. It has photons. But this to me looks like those photons are traveling pretty straight. This is how I would draw it. Ooh, fancy. Light waves, light waves. Okay, you get the point. Alright? Now I'm going to say something that's going to blow your mind. You might want to hold on to something. Okay? So, Einstein's equation essentially says anything that has energy, that's traveling, has mass. Can we invert that question? Anything that has mass, you, me, this tennis ball, this bottle of water, anything that has mass and is moving is traveling in a wave. Yes, it is. Okay? I know you don't believe me. Let's do a little visualization here. I want you to imagine yourself walking down one of our hallways in this building. Okay? You're not running, you're just walking down the hallway. I feel like I'm walking pretty straight. But I'm not. I'm walking in a wave. Why doesn't it feel like I'm walking in a wave? Something about my wave, my travel, is extremely small.
Amplitude.
Not the amplitude, the wavelength. Okay? I actually went and calculated this yesterday. I used my husband's math because I didn't want to use my own math. I just felt funny about that. Because then I thought someone would go and like back calculate. Okay. And would you say that like if I'm walking at about this pace, it's about a meter per second? Close. Okay, well that's the speed I use. So I used my husband's math. Imagine he's walking at a pace of about a meter per second, calculated his wavelength, which you'll be able to do next 2 classes from now. His wavelength, 6.4 times 10 to the negative 36 meters. Do you think you could detect that with your eye? I don't think so. No, you couldn't. All right? When a pitcher throws a baseball, it looks to you, looks to me like he's throwing it pretty straight. He's not. Okay? He's throwing it in a wave. And then there's always someone who's like, what if we're watching it in slow-mo? No. You're not going to be able to see it. What if it's shot in HD? No. Okay? 3D? No. Okay? You're not going to be able to see it.